type of situation where it's just a generalization. Here's my y-axis, here's my x-axis. I have rotation about the x-axis, right, x-axis. And I've got this positive function up here, f of x. That means that any y partner on this curve will correspond to the y value on the y-axis is f of x. Now I'm going to take a portion of this curve from x equal a to x equal b. I'm going to rotate that about the x-axis. So I have something that I call the rotation arm. The rotation arm is the distance from the axis of rotation out to the curve. So in this situation, the rotation arm for this positive function f of x is equal to f of x. And that picture gives us the formula for the surface integral. It's equal to 2 pi times the integral from x equals a to x equal b of the rotation arm f of x times the square root of 1 plus the derivative of y with respect to x squared dx. And that radical is something we developed in class. Now, I want you to compare that to this example, where now we have rotation not about the x-axis, this is my x-axis down here, but now we have rotation about a line y equals c, so it's this line, y equals c, that's our axis of rotation, and our function f of x is going to be less than y equals c, so this is the line y equals c. So we've got this function down here, and we'll pick a point on there. That point, since the function is f of x, that point corresponds to the value f of x on the x-axis. Alright, so now what's the rotation arm now when we're rotating about the line y equals c? Well, this value is the rotation arm. So in this picture, the rotation arm is not equal to f of x. It's equal to the distance x equals c, so it's c minus the f of x. Do you see, if you look at the picture, you'll see that x equals c will give you this entire distance, f equals c, f of y equals c, but then if you subtract this distance, which is f of x, then you'll be left with this distance, which is the rotation arm. In that situation, the surface integral is 2 pi times the integral from, of course we have our a here, and we have our b here, so it's from a to b. Now, remember, in this situation, the f of x was the rotation arm. In this one, the rotation arm will be c minus f of x times the rest of the integral, 1 plus dy dx squared dx. So what we see is different is this part, the rotation arm. Okay, so we see an example in the book, example for homework number 32. In that situation, we have the line y equals 4. Y equals 4, and that's the axis of rotation. And we have a function, y equals x to the 1/2 power. In that situation, since we're rotating about the line y equals 4, the rotation arm will be this distance, and the way we would express this distance is rotation arm is equal to 4 minus f of x, which is the square root of x. So that would imply that the surface integral for this problem is 2 pi. Again, we're going to go, well, here we're going from 0 to x equals 4. So it's the integral from x equals 0 to x equals 4 of the rotation arm, which is 4 minus the square root of x, times the square root of 1 plus dy dx squared dx. That's how that problem is done. We didn't have to do that one, but that's how that would be done. Now let's look at the example that we're interested in, example 33, where we have the y-axis, the x-axis, and we have a circle of radius r centered at the origin. So this is r, and we're interested in rotating about the line y equals r. And we said we're going to break it up to the top and the bottom, so first we'll do the top portion. In that situation, here's y equals r. And we have rotation about that line, and we only have the top portion, the top half of the circle. It has the equation y equals a positive square root of r squared minus x squared. And this little portion here, this tiny little portion, is our rotation arm. So that little piece in there is our rotation arm. And that is equal to r minus f of x, which is the square root of r squared minus x squared. So you would plug that into the formula in place of the rotation arm, just as we did here for this rotation arm. Okay, and then doing the bottom portion, the bottom half of the circle, down here, this has a formula y equals negative square root of r squared minus x squared. And then we have our line up here for the rotation. This is y equals r, and we're rotating about that arm. So now the rotation arm is this long value here, from this point down to the function. So that is our rotation arm. And it is equal to r plus, well, we're going to add this portion down here, and that's going to be the absolute value of y, or f of x, where we're only looking at the bottom half of the circle. So that's equal to r plus the square root of r squared minus x squared. Okay, so we took the entire r distance here, and then we added to that the entire absolute value, which is the distance of the y function. And that gave us our rotation arm. So in one case, we have the surface integral for the upper half of the circle equal to 2 pi integral from negative r to r of the rotation arm r minus the square root of r squared minus x squared, and then times the square root of 1 plus dy dx squared dx. That's for the upper circle. And then for the lower circle, we have s equals 2 pi integral from negative r to r of r plus the square root of r squared minus x squared times the square root of 1 plus dy dx squared dx, which uses the other rotation arm.